Well, good day to our viewers and our listeners. Welcome to Ep07 of Light Conversation. Welcome, James Portman.
Hi, Phil. Nice to see you again.
Good, thank you. We are back today in Light Conversation discussing a very interesting topic. And the topic today is around lasers and eye safety. What are those characteristics that we can manipulate in a laser to ensure that we remain eye safe? We're working with a very small factor laser within our micro LiDAR devices. And what are the different things we can do to manage eye safety within these devices? I'd like to kick off, James, and as always, the objective is to catch James out with some tricky questions. So let's see how we can go today. I'd like to kick off with classic energy equation, because, if we think about safety, I think about energy. And going back to engineering days, kinetic energy is half mass v squared. Now, if we look at light, light is composed of photons, and photons have no mass. So now we substitute into our little equation the fact that there's a zero for mass, and we multiply it by twice times the speed of light. We've got zero energy. Now, how is this possible?
Well, the mass particle and wave duality issue is something that has challenged the greatest minds on the planet. And as an engineer, needless to say, I don't care so much exactly how it works. I care more about what it actually does and what it means for practical products. So whilst we can delve into the realms of quantum mechanics and try and understand this nature, I think the important thing to recognize is that photons do carry energy, and that they're not just things that are just flying around and don't mean very much. Because as human beings, we rely on this energy in order to, for example, see. So the photons will impinge in the sensors in our eyes and create a chemical reaction, which allows us to recognize objects and see what we're doing. But as advantageous as that is, we also have to be extremely aware that if we stare at the sun, for example, there is just too much energy. So it turns out there are multiple factors at play here. This is not only the energy of a single photon, for example, which turns out to be proportional to its wavelength. Shorter wavelength photons carry more energy. But it's also the bulk effect. What about a whole lot of photons together? Do they carry a lot of energy, or is it just purely individual? And it turns out that that bulk effect is very important. And in fact, single photons, whilst they can be dangerous, particularly at very short wavelengths when you go right down to X-rays and so on, generally in the visible spectrum and the near-infrared spectrum, which is where most LiDAR devices work, it is the group effect that is more important than the individual effect. So whilst wavelengths do determine the energy of the group as much as it determines the energy of the individual, it just simply means that you would prefer to use a longer wavelength in the group of photons that you're going to send out of your laser. However, I think this is where the interesting part of the subject comes about, because it is not just about the pure rules of physics here. We are talking about the interaction between energetic particles and biological systems. Now, this is what we have to be really careful of.
Right. That's intriguing. I love that little segue. There's a couple of things in what you've said right there. And, I've been reading a very interesting book of late, a short history of just about everything. And one of the discussions, and obviously we're talking about moving into this realm of quantum physics, and, where Einstein's equation of E equals mc squared came up. And, the fact that if I take my mass and, the energy potential within me as a human is equal to like 3 massive hydrogen bombs, just all locked up within the quanta of my being.
Yeah.
And sometimes I think we really forget the amount of energy that's locked up in the entanglement of all of these different particles, and we're really dealing with a tiny little subset of the entire potential energy of of a beam of light, and how catastrophically things could go wrong if it's mismanaged, and how much there really is to work with in terms of really guiding and managing this energy in terms of delivering the right kind of light at the right frequency at the right level of energy. Maybe just before we go,
if I may make a comment on that, this is really important because before the 1960s, light was relatively harmless. The only thing you could do was to use it to heat things up. And that was through magnification, by basically collecting more of it. But as we've moved into the realm of lasers, suddenly that quantum energy that you're talking about has become accessible to us. And whilst it looks like a very small device that you can just buy on DigiKey and you say, oh, look, here's a little laser. What is going on inside that laser is right down at this quantum level you're discussing. So the energies are enormous and you have to be very careful how you handle them.
Right. Let's take a second and just recognize Mr. Max Planck. This is the relation, and I think just for the benefit of some of our viewers, the relation between, you mentioned that the energy of a photon is proportional to its frequency. And that's the famous equation E equals HF, where H is this Planck constant. Maybe just offer us a couple of comments on that. Any comment?
Well, again, I like to steer it towards the engineering application of equations like that. It's basically saying that whilst you may have less energy by running lower frequency light, that means a longer wavelength, remembering that they are proportional to each other. It doesn't necessarily mean that you'll have a system that is less efficient or less capable. Because in creating those particular wavelengths, you may find that there are engineering optimizations that work in your favor. So you may say, you may discover that a particular material, let's say gallium arsenide or some other substrate, produces infrared light, which is a longer wavelength, much more effectively than it produces, let's say, blue light. Now, when you're trying to build a system like a LiDAR system where you want to project that energy, then having a decent and efficient energy source is really important. So it turns out that often you will pick the wavelength that matches the fabrication of the laser device rather than attempting to build a laser to produce a specific wavelength, if you know what I mean. Because it turns out that not all materials will produce all wavelengths. And this has been one of the big challenges in the world of laser development, is to get what you want out of a system. And we mentioned a few episodes ago about not only must the laser produce the right wavelength, but the detector must also be sensitive to that wavelength.
Right. And that's why lasers mostly, we've always seen green lasers and, then we have blue lasers and, it's all a function of not so much the ability of a laser to be a certain color, but, how the silicon substrates and the different materials are able to work at an atomic level to produce and generate that frequency of light.
And of course, here is where the complexity comes in, because eye safety and biological safety turns out to work on a completely different set of equations than the chemistry that goes into manufacturing a laser. So you may find an engineering optimum at, let's say, green wavelengths or red wavelengths or infrared wavelengths with certain materials, but you may then discover that biologically they are particularly harmful or particularly safe. So as a general rule of thumb, the longer the wavelength, the more biologically safe lasers are. But it turns out that it's not a single dimension, that in fact, biological systems are exceedingly complex. Therefore, whether it is the average energy that impinges on your skin or the peak energy, or even the frequency of pulsing of a device, each of these evokes a different biological response. And when you're attempting to prevent biological damage by making eye-safe devices, you have to take into account all of these different dimensions. So suddenly a human being and animal matter in general becomes part of your engineering equation. And I think a lot of people totally underestimate this when they get into the world of LiDAR for the first time. They're so used to looking at the electronics, let's say, or the optics of the laser devices, only to discover that once they've made a super efficient and super effective system that is horribly unsafe because they didn't take into account the biological consequences of what they were doing. So it's a more complex network than you think.
Let's take, yeah, it is. And, I can imagine, taking my fluke ammeter and applying that to, a measurement coming off my inverter. I mean, it's a very absolute measurement, and it's within the confines of understanding, right, here's the current, here's the voltage. But as you then translate that into a human biological system, it does become a lot more complex. We have an amplitude adjuster. We have all different kinds of mechanisms within our eyes that protect and respond. Before we move to that, maybe let's just take a snapshot in time and encapsulate and I don't want to use the word beam because it's not that, but a package of light. What are the different things that, we've spoken about wavelength and frequency of the light. There's, and you also mentioned that it's a number of different factors that work together in terms of the energy that's emitted. Now, the other obvious one is pulse length. So, if it's a microsecond as opposed to 2 seconds, there's a whole lot of different light coming down. Now, it runs over a course of time, but what is the variability there? If you did the same flash, if you flash at 100 milliwatts over 2 seconds, is that the same as flashing, half a milliwatt over 4 seconds? And then the other thing then is amplitude, right? And if we look at how strong the wave is, can that be equated to the brightness of the beam? And what effect does that have? So maybe just, I don't know if there's anything I haven't mentioned, but looking at the different components of the carriers of the energy around the photons traveling in waves, maybe just run us through those and just give us an idea of the relation between time and energy on each of those different dimensions, if you will.
Yeah, this is an extremely complex characteristic set that we're looking at here, because in the end, it's about the biological response, and you almost have to look at that first and then work backwards and say which parameter triggers that biological response. And it turns out it's everything. So, for example, the beam could be a narrow beam or it could be a wide beam, but have the same energy. What that means is the beam has different energy density. If you like, localized intensity can be different. You have to take that into account.
Yeah.
And it turns out that most laser beams don't generate uniform beam patterns anyway. So you would have to examine an area within the beam matching the size of the pupil of the eye for the type of period that you're expecting it to be on, and so on. Then, yes, the length of the pulse makes a big difference because biological systems take time to respond. And sometimes it needs a few seconds of energy before it does anything. At other times, it can respond in nanoseconds because it depends on the nature of the damage that's being caused or the effect that's being caused. By the same token, the peak power obviously plays a role. If you look at laser cutters, they often work with very high peak powers, though the average power might not be that high. But you can do the opposite as well. You can run with very low average power and very high peak power, and it can still be eye safe, depending on the wavelength, because obviously each photon is affecting the biological system in a different way. So the real complexity here is finding the right combination of parameters to give you a good result. And I've got to tell you, I think that there's a lot of mumbo-jumbo going on about this in the world of LiDAR at the moment. Everyone is saying, if I have a 1550 nanometer laser, I can push as much power out as I like and it's going to be eye safe. This is simply not true. It turns out that if you pulse that laser faster, it gradually loses its eye safe characteristics. At low frequency, yes, it's almost completely eye safe, but at high frequencies, it's not. Similarly, people will say, well, we've got a shorter wavelength device, let's say 850 nanometers or 905 nanometers, and we've adjusted it so that it's eye safe, but we can only pulse it slowly. That's not true. It turns out you can pulse it almost as fast as you want, and it remains eye safe. So in other words, it has exactly the opposite biological characteristics to a 1550 nanometer laser, where there, if you up the frequency, it becomes less safe. Whereas if you're at 850 nanometers, as you up the frequency, it doesn't make any difference at all. So these characteristics are what are called nonlinear, meaning that they are, in some ways, they are stepwise nonlinear. So it's not even as if it's a simple equation. You actually have to go and do the tests. And this is what the FDA does and various other standards authorities do. Right. And they create the standards that you use to determine whether your system is safe or not. Also, if you have a scanning beam as opposed to a static beam, it makes a difference because the possible exposure time changes. You can also have short trains of pulses with long gaps between them. The pulse width could be anything from 1 nanosecond to 100 nanoseconds to 1,000 nanoseconds. And again, depending on the wavelength, has a massive effect. My suggestion is to people who are getting involved in this field is to buy one of the really capable analysis applications that you can get, feed in the parameters of your system, measured correctly and so on, and verify it against the human model that's built into these applications. It's really the only way to be sure that what you're building is completely safe. Yeah. So not a trivial thing to do at all.
Yeah. And then obviously real world testing. I mean, I know that within Lightware, we do a huge amount of real world testing in various conditions to verify the theoretical standpoint of eye safety. Let's consider lenses for a second. As kids, we used to play with magnifying glasses in the sun and chase down ants. And given a constant light source, the sun, you could have a very successful effect on the game you were playing or not, depending on the level of focus of the beam. So how do you apply focus within a LiDAR laser light system to manage beam strength?
Yeah, that's very important as well. Generally, what you find is you can use the lenses to spread the beam over a wider area, and that reduces the energy intensity of the beam. And often a beam that is extremely narrow may be not eye safe for whatever parameter is your limiting factor. However, by spreading that beam out, it may become eye safe. However, do understand that there's nothing to stop somebody picking up a pair of binoculars and remagnifying the beam back down to a sharp point. So the different laser classifications take that into account. So for example, a class 1 laser can be viewed with magnifying devices without exceeding any eye safety limits. Whereas a class 2 laser, for example, or 3 laser, you absolutely cannot use magnifying devices because they will cause damage. So again, this has to be taken into account. And I think once we start delving into the world of optics, again, it's a very powerful engineering methodology of controlling the beam and getting the result that you want in terms of performance of the LiDAR as well as safety that goes with it.
Yeah, absolutely. And I think, I remember learning this for the first time that, most of our LiDAR, well, all our LiDAR devices actually are class 1 eye safe. And that means not only is it safe to look right into the LiDAR device, but you can actually take a pair of binoculars. So, from a normal use perspective, it's actually extremely safe.
Yes.
And is there anything else you want to add at this stage, James, in terms of this topic? Because I'm feeling that maybe we can leave over till next week the discussion around optics, because that might be a very nice next topic.
Yes, I think you're correct. I think this kind of naturally leads on, where suppose you have managed to build your device, you have got it within eye safety parameters. How do you now get good performance out of it? And what do you actually do with the beam? Because you've simply created a beam now, but how far will it measure? What will it measure? And what changes to optics will affect that?
Great. Well, thank you very much. I enjoyed that conversation. It's very interesting. I look forward to next week, where we can discuss optics, lenses, different kinds of lenses, beam distortion through optics, And how are you able to apply a laser at 10 centimeters and at 200 meters and be able to, with varying levels of intensity, do those measurements? So I'm sure that will be an interesting topic and of value to our listeners.
I look forward to it, Phil.
Great. Thank you for your time, James, and we'll see you next week. If you're watching on YouTube, please hit subscribe. Otherwise, visit our website, www.lightwarelidar.com. Thank you.